Hi, everyone. My name is Brittany Joyner, and I'm a software engineer at Elastic. I've been here for about 4 years, and I like Elastic so much that I ended up naming two of my stray cats after Kibana. And the reason for that is one of the stray cats lives right outside my door and is nearby about 99% of the time, whereas the other stray cat lives somewhere else around here and comes and visits me periodically. So I call the first one KP for Kibana on-prem, and the second one is KC for Kibana Cloud. But we're not here to talk about my cats. We're here to talk about the actual Kibana and all of the Elastic platform. You've just gone through and seen all of the new features we've added in version 7 and more recently in version 8. And for the next 20 minutes, we're going to talk about all of those features and bring them all together to see how they help you search, observe, and protect. We're going to assume a common use case of an online retail store. So as an e-commerce store, you're going to need a way for your potential customers to find products they're looking for. To do this, we'll be using enterprise search. In addition to that, we also want to monitor the behavior of our users on our website to make sure that they have the best possible experience. So we'll be using Elastic Observability to monitor the performance of our applications and servers. And lastly, we'll be using Elastic Security to prevent, detect, and respond to threats. All right, so let's get started. So we're going to start by talking about enterprise search. And Elastic allows you to build search for any application easily. In the context of online shopping, search is critical to helping customers find products that they want to buy. In our example, we can see that Elastic brings all of the search features teams need to build a rich search experience for customers who want to find products on their website. Let's start searching for clothes here. Notice when I type jeans, we're immediately presented with suggested queries and results. Notice the speed of the search query performance, another critical factor for customer experience. From there, we can choose to execute our search query, or we can pick from one of the suggested items here. Let's execute the query by just pressing enter. Here's the search results page. Check out all of the e-commerce search features we expect brought to you by Elastic. Search users can review detailed search results, sort according to different criteria like prices or relevancy, or they can filter results based on generated facets like colors or other properties. Everything they need is right here. While searching with keywords is the most common way for customers to search for clothes online, technology evolves, and we want to be a step ahead of that. We can offer alternative ways for consumers to find products they like, offering them even more convenience. Powered by the most recent KNN search feature developed by Elastic, we can offer visual search to our users. We use K-nearest neighbor search to find the nearest vectors, such as images, for a given image measured by a similarity metric. We can then upload an image that's processed by the model and compare it with all of the other images in the data set. Now, imagine you find a piece of clothing you like online. You might not know how to describe it in a way that'll help you easily locate the style in your favorite online store. The fastest way to locate a similar product is to upload an image of that product to your e-commerce website. Elastic finds similar products to the one you like in milliseconds. So let's try out an example here. I found this blue dress on Instagram, and I'd like to see if my favorite store has a similar look. If you know me, you know I only shop for dresses for the sake of an Elastic demo. So I'll upload the photo of the blue dress, and I'm presented with similar products in the store. Notice that I can still make use of all of the other search features like sorting or filtering results. One of the benefits of using Elastic to build e-commerce solutions is the ability to automatically collect analytics, such as popular queries, popular results that were clicked on, and the position of popular products in search results. These analytics bring valuable insights to search user behavior that an analyst can use to fine-tune the relevancy model to bring better results to customers. Elastic goes one step further and automatically suggests relevancy model adjustments based on recent analytics data. This saves your team time so you don't have to actually go find them all yourself. So let's take an example. Imagine that users searching for jeans often click on a specific result. Let's type in and see. Well, let's say that they click on this result right here and they ignore all of the other results. Wouldn't it be even more convenient for customers if we showed this result at the top instead? So let's go to the admin part of the Elastic platform where we can review our site analytics and tune the relevancy model. You'll see here that we can quickly review out of the box analytics, including top queries, which tell us what are the most popular search terms on our website. We can also see top queries with no results, which is a great indicator that we're either missing products or we have some relevancy model issues that we need to fix. Moving on to the curations, we can review some suggestions made automatically by Elastic. All right, so you see here, we have a suggestion for a new curation for the term jeans. Let's click on that. So we can see that we don't currently have a promoted result for that query, but we do have a suggested promotion. This suggestion has been made based on the user analytics reflecting the strong performance of this specific result relative to the query. We can see more detail and also test the search to see what the user would get as a result for that query. Let's just check through all of these here. It looks like a good suggestion, so I think I'm going to accept it. Note that we have the choice to automatically accept all suggestions if we want, or we can handpick them like I'm doing right now. Now we can see our promoted document on top of the list for that specific query, making it easier for consumers to find their favorite products. In this next section, we're going to use natural language processing to enhance the search results for a customer support use case. So let's assume we bought a product in the e-commerce store, but we didn't get the product after several weeks. We decide to go back to the store website to seek out support and head over to our helpful chat box over here. The chatbot replies to the question, but the answer isn't relevant to what we asked. However, the bot does offer a link to get more information. The page that opens is a search results page that shows keyword matching results using Elastic as the search engine. We can see that the results contain the keywords we used, but the results don't contain the full context of the question that we put in the chat box. Elastic has an alternative way to search for the results by analyzing the natural language in the search box. Let's look at those results by clicking on this brain icon. So you see, we don't actually match many keywords in the search. You can see this by the yellow highlights here, but the first result in the list is actually a perfect answer to our question. With Elastic Operators, we have the ability to tune every aspect of the search experience to the customer's needs. We need to ensure that the customers have the best possible experience on the website. So we're using observability to monitor the end user experience as well as the performance of the applications and servers. Using observability, we'll investigate a performance problem that we've been having with our database. To help with our investigation, we'll add an additional data source on the fly. So let's head over to our alerts page, and we'll see that we've just gotten some alerts showing that some of our services are experiencing a higher than normal response time. In addition, our synthetic monitoring checks also notice that something's wrong. The service map shows several unhealthy services, and it looks like they're all calling this product catalog service. So let's start our investigation there. As we can see, the response time of the service is higher than last week, and we see our alert annotated on the timeline. The increase in latency doesn't seem too severe yet, and we also don't have any failing transactions right now. So at least the end user impact is limited, but let's keep looking. As we scroll down a little more, we see that the Postgres database seems to be responding slowly. Taking a closer look, we can definitely see that the latency of the data set went up by a factor of 5, which is not good. We'd like to continue our investigation in Postgres now, but unfortunately, we don't have any log or metric data for Postgres. So let's change that. We already have Elastic Agent collecting system metrics from the host that Postgres is running on. So all that's left to do now is enable the Postgres integration. To do this, we'll just add a new integration to the existing policy. We just need to search for Postgres and click through the setup wizard. Once the integration has been added, we can use the out-of-the-box dashboards that come with the integration to look at the data for Postgres. Give me a second to bring it up here. Okay, so check this out. We're already receiving new metrics, and we can see that PG Bench is running against our production database. That's not good. Looks like someone might have used the wrong host for benchmarking, and that could explain our performance anomaly. We've just seen how easy it is to use anomaly detection and alerting to identify and investigate performance problems. Even though we didn't have all the data we needed initially, we were able to quickly add the missing pieces to find the root cause. In this next section, we'll be looking at a slow checkout page on the website, and we'll use APM correlations to find out why it's slow and see what we can do to fix it. We mentioned earlier that we can add products to the cart and then place an order. This process should be as quick and easy as possible so potential customers are happy. One issue right now is that the page currently has the checkout process being really, really slow sometimes. Take a look. Yeah, this is far too long. Let's use Elastic Observability to figure out what's causing this and what we can do to prevent a bad user experience. We're starting off on the service map, which gives us a view into the dependencies and health of the services that power our platform. Since we already know that our issue is impacting the checkout process, we can start our investigation over there. Let's head on over. Yep. So at first glance, everything looks pretty normal, but just to be sure, let me increase the time span we're looking at to the last 24 hours to make sure we're not missing anything. We can see that the service is only doing a single type of transaction, and that's the place order function. Looking at the transactions of this service in more detail, we can get a good breakdown of the latency. We're getting some failed transactions in this view as well, but all of them tend to fail quickly. There's a second peak towards the right side, which looks interesting. So let's see what we can find from there. We're able to select this peak and filter down to just the transactions with a response time in that range. Before we look at the performance of the trace, let's take a quick look at the logs associated with it. With just a single click, we can view all relevant logs for this one trace across all of the services that were part of this transaction. But it looks like there's not much of interest in here. It's just info logs that look pretty normal. Going back to and scrolling down the full distributed trace, we can see that this service is talking to multiple other services to complete the checkout process. Most of these services respond within a few milliseconds, and they're therefore also not the problem. Things start to get more interesting towards the end of the trace. We can see the checkout service calling another service, which then talks to a fraud detection service, and that request is really slow. First off, just connecting to the service takes a long time, about 4 seconds, and then the service itself is slow as well. This could be what's holding us up, but let's dive in a little bit more. Here we can see that this service encountered what's called a cold start. This service is running in AWS Lambda, and it's not used frequently. So that means that sometimes when we call this service, it needs to be started first if it hasn't been called in a while. On scrolling down here again, we can see this second peak with the same slow performance as before. And we can also see that the one sample trace we're looking at right now is also tagged with a cold start label, indicating that it also ran into that cold start scenario. If we now want to figure out if all traces on the right were a cold start, we could do a couple things. We could look through them individually, or we could filter down as we were doing before. But an even quicker way to do this is to use the latency correlations feature. So this looks at all of the associated metadata to find information that's interesting. What makes the slow transactions slow? Is there any value that's part of these slow transactions that we don't usually see with the quicker transactions? In this case, we have a very strong correlation of 0.98 between the slower transaction, each having this FAAS.coldStart equals true value. As we can tell here, all of these slow transactions are caused by a cold start. And this wraps up our investigation. We've just gone from the service map, which showed the dependencies between our dependencies, into the services, then found that the serverless fraud detection service is the problematic service causing these occasional latency spikes. Elastic security can be used to prevent, detect, and respond to threats in the environment. In this last section, we'll show you a recent Log4Shell exploit investigation. We'll also be using Workplace Search to help with the investigation, as well as OS Query to make sure no other hosts are affected. As we conclude our work in the Observability app, we notice a new dependency popping up in our service map. As we've never seen this host before, let's turn the situation over to the security team for additional investigation. Because we're using Elastic Security, our SIM has access to all of the data utilized in the observability solution, giving us visibility into the applications. In addition to the observability data, Elastic SIM provides integrations with hundreds of security-focused data sources. We're collecting our security data with various Elastic Beats data shippers, as well as Elastic Agent integrations. This is the same Elastic Agent which includes our Endpoint Security's Advanced XDR, which protects against host-based threats across all major operating systems. Before we take a look at the broader picture, let's deal with our latest threat. We can see 3 alerts in the time range from the service map screen: a malware prevention alert, a suspicious Java process, and a correlation rule indicating suspected log4 shell activity. Let's start with the malware prevention alert. The first thing I see when looking at the alert is that Elastic Endpoint Security has prevented malware from executing. Checking the alert details flyout, I can quickly evaluate the potential risk of this alert, as well as immediately isolate the host if necessary. Towards the bottom, we see the relevant threat intelligence data and an aggregate alert risk score for this host. Given the score here, I'm definitely thinking investigating further will be necessary. And for the time being, I'm going to isolate this host as it doesn't look like a typical production system based on the host name. If I switch to the event rendered view, I get a better understanding of what exactly has happened. And moving to our graphical analyzer view, I can clearly see that a Java process has executed a shell command attempting to download, modify, and execute a file that's been identified as malware. Now, if I check the suspicious Java child process alert, I can see these alerts are definitely related as they're referencing the same attempt to download and execute the malware. Now, the third alert is a rule we've created to alert us to sequences of behaviors that are indicative of this type of log4 shell exploit. Changing the alerts view filter to add building block alerts, we can see the specific events that make up our correlation rule. We're looking for a combination of suspicious Java child processes, malware alerts, and a subsequent network connection on ports commonly used by the JNDI service. We can leverage hundreds of pre-built detection rules as building blocks to create custom correlation rules for our environment. This is a quick way to cut down on the overall number of alerts that analysts have to triage. At this point, I'm still a little unsure about the host. While it's operating in the production environment, the host name field suggests this might not be an actual part of our production application. Fortunately, we're also running Elastic Workplace Search, so I'll just run a quick search and see what I can find about this host across our various information repositories like SharePoint, Google Drive, Jira, and GitHub, for instance. A quick search provides me with a GitHub issue. As you can see, this host is apparently a development server that's been installed as a stopgap to address some issue with advertisements. As such, I'm going to leave it isolated and move on with my investigation. So now we can build our investigation in a SIM timeline, then open a case to manage the investigation. Clicking on the Investigate in Timeline link from the alerts page lets me start my investigation. Behind the scenes, a timeline template extracts details from the alert and sets up the appropriate view and filters to let me hit the ground running. From here, Timeline lets me drag and drop just about any field value pair into my query builder to do all sorts of things. I can easily pivot through data, I can expand our search with information from the results, or focus on specific events or time ranges. I can then pin those events that tell the full story. Expanding our data view to include APM transactions and our searchable snapshots frozen tier, we can quickly search for other log4 shell indicators of compromise with terabytes of archival data retained in cost-effective object storage that were collected in the past few months. This is a good practice to ensure that we haven't been compromised in the past. Additionally, because we have OS query running in our Elastic Agent policies, we can quickly scan all of our hosts for running processes that are vulnerable to the log4 shell attacks. Right now, it's just the one, but it's probably worth scheduling this search and creating a dashboard to track these IOCs. At the end of the day, we're analyzing more data, more cost effectively, and more efficiently across every aspect of the organization: users, hosts, network, cloud, and custom applications. Elastic Security makes this possible by deploying centrally managed agents throughout and saving the right data for as long as we need, enabling a truly unified SOC experience across development, operations, security, and the business. So thanks for joining me today. Hope you enjoyed and learned a few things along the way. And next up, we have Matt Riley talking to a couple of our customers about how they're actually using Elastic. Over to you, Matt.